Now, okay, so today is the second class of the Big Data Analytics. We will cover a little bit more lecture that is left over from last class about the nature of data and so forth. But most of the class today will be spent as a beginning tutorial, sort of like how to get started with Mathematica. So let me show you again that when you start Mathematica, it should look a little bit like this. So you guys can see the screen, right? Okay. So when you start Mathematica, okay, it's initializing the kernel and whatnot. Okay. So depending on if you have something previously, you can start a new document. Now, the document I want to work with is basically the class notes. So I will just simply double click it. So today I will mostly spend the time on the tutorial. So this would be the tutorial sheet that I prepared for this class. Okay. So these are the essential tools within Mathematica. These are 9 topics here. Language primitives mean the very basic things of how to get going. Mathematica is mostly based on what's called functional programming paradigm. There are, if you have friends from say computer science, you know that programming takes many paradigms. Paradigms are sort of like styles of telling a computer what to do. Okay, so declarative programming would be saying a very high level. I want to do this. Find me a way to do it. Functional programming would be like creating a function. So representing computation as if it were a sequence of mathematical functions. Okay, so f of x, and maybe you have f of x and so forth, and f of x, y. So all the computation is equivalent to writing a series of mathematical functions. Okay, so that would be a functional programming. Procedural, that would be like telling the step, you know, for step 1 to 10, do this, add that, blah, blah, blah. So like procedural. And there's also like object-oriented programming. This is a little bit more like you wrap all the functionality into a class of object. Say this object performs certain kind of function, store certain kind of data, and to work with it, you have to make a request and say, okay, please remember this set of data, please retrieve this data, please do something to this data, and so forth. Okay, so those are different mathematical, different computational or programming paradigms. Now, for those of you again who are just who are taking this class because you would want to apply it perhaps to your domain topic, which could be like sustainability or smart cities or health science, and you don't want to go into the full-fledged data analytics, applied digital intelligence track. You may not need to know, say, a language like Python. Okay, Python is more ubiquitous in the workplace. Now with Python, it supports many kind of paradigm, but it works mostly, or it works best for most user of Python would use functional programming paradigm. Okay, and Mathematica is really framed around that. So the logic would be quite similar to the majority of Python code out there. But this is a higher level. It's a higher level, so it's suitable even for those who are not going to become a real programmer, because you know it's kind of like assume some of the nitty-gritty environment building thingy about that you need to do if you want to write like a full Python code. Okay, so it's easier for a non-programmer to learn. It's more high level. On the other hand, it's also more powerful mathematically, but that's not the reason I'm using it in this class, because this class is not using very powerful mathematics. Okay, just using data analytics and some machine learning algorithm, which you know these days are not considered that advanced mathematics. Okay, right. So we're going to go cover the language primitives Now, the user-defined function is a very important part because, like I said, we express all the steps. Whatever we want the computer to do, we instruct it in the form of function. Okay, so instead of saying, please do this for me, you would create a function that represents that instruction set. And when you call that function, then the computer does that thing for you. Okay, so you have to, so not only are there built-in functions like mathematical function, there'll be user-defined function. Okay, so I make a distinction between mathematical function that you learn in high school or in college, you know, sine, cosine function. Those are standard mathematical function, exponential, right? Logarithm, or these are all standard mathematical functions. But you are going to instruct computers to do things by creating a user-defined function. So that will be the bulk of what the programming is all about. Now, data analytics begins and ends with visualization, believe it or not. Even if you're building very advanced machine learning models, chances are you tend to start by just looking around and see what kind of feature, what kind of stylized fact you can draw about your data. So you have to sort of like visualize, and a lot of it has to do with, a lot of it can be done with what's called just plotting function. So you plot the data, you sort of like display the data, you try to figure out what it is. The manipulate function, this would be something like very useful for those of you who are trying to prototype an application. So if you think of like an iPhone, right? An iPhone has buttons to do this and that, and you have a function. Well, when you create an app, you have some kind of user interface that user can control. You know, push a little button, turn a knob, and so forth. Manipulate function is a mathematical way of prototyping those functionalities. You know, like turning a knob, increasing this, lowering that, and so forth. 5 and 6 is about the inherent mathematical capability that deals with calculus. Okay, so this is something that I may skip over in this class. I may show a little bit. Okay, solving equation, however, is very ubiquitous. Even if you're not going into advanced problems, sometimes you want to find in your application some kind of constraint relationship. You know, you have some kind of demand, some kind of supply, some kind of production schedule. You want to solve, you know, system of equation. And so that's what solving equation is all about. And optimization takes it a little bit further. When you solve an equation, okay, when you solve system of equation, you likely get a unique solution. In fact, in all your lives, in high school, in grade school, when teachers give you mathematical problem to solve, there is a unique answer. Okay, they design it that way. But in life, I tell you this, it's very rare that in real application, you will run into a situation for which there is a unique solution. Okay, let me say that again. The situation that you've been trained for all your life, you know, having some kind of system of equation and solving for X, solving for Y, that is rare. That is rare. In real life, you will encounter two situations. One, you will not be able to find solution. In other words, the problem is not feasible. It cannot be done. It cannot be done. Okay, it's like you're trying to satisfy too many things at once. So how do you get around it? You have to re-engineer the problem or the solution. Okay, so that's where you go to engineers. In other words, this is not workable. It cannot be done. It cannot be done under this requirement. Too much demand, not enough supply. Go to engineers, increase production, do something with the real system. The other situation you run into is you have more than one solution. The point is that even though you have more than one solution, some solutions are nicer than the other. They are nicer with respect to some decision criteria. So there are 100 different ways for you to drive from Bangkok to Chiang Mai. Okay, so it's not a unique solution, right? You have multiple solutions, but you want to choose the solution that gets you from here to Chiang Mai in the shortest time. That will give you one route. with the least amount of gas, with the least amount of carbon footprint, will cost you the least, cheapest. All these are different criteria that would allows you to optimize, choose the optimal solution amongst all the solutions. And that's what optimization is all about. Okay, now, all these are essential tools. They are not the models themselves. These are basic fundamental tools. And one of the fundamental tools that you will need for this class is how to deal with data. So we're going to cover a lot of that perhaps today, more than other topics, more than other days. Okay, so how do you handle data? Because you're going to apply tools or models onto data. That's what data analytics is. Even to visualize, even to do plotting function, right? You're not plotting any function that you dream up. You're plotting data that you get. So how do you get the data from a flat Excel file into a form that you can visualize and so forth? Okay, so today is all about essential tools. Okay, all about essential tools. Now, I want to actually pause the record a little bit, because this morning, not this morning, today, a few hours ago, there is a new introductory video on the Wolfram language, which I thought is very friendly. Okay, so what I'm going to do is going to play this, because it's only 10 minutes, so I think it's worth it. Okay, so let's pause the video a little bit and we'll go to this. And oh, by the way, I apologize that I did find a microphone, but it doesn't work, so I ordered like a headset. So maybe next class I'll have that. Okay, but so I want you to watch the big data. Okay, so let's go back to the mind map that we did last time. If you're talking about big data, okay, there are three attributes to it. Velocity, okay, that just means it comes in quick and fast, and you need to do something quick and fast. It's a little bit about performance kind of thing, right? Volume, that's also about computer performance and capacity. So these two things are sort of like engineering issue, okay? Engineering issue. But what is relevant to you, okay, as a bioscience student is this part here, is the variety. Now, the velocity and the volume requires some kind of technology platform. And that's why you have things like MapReduce and distributed storage, some kind of EFS and Hadoop and so forth. Okay, so all these are important because you're dealing with volume and also velocity. Okay? But for this class, since you're not going to be a professional computer engineer, okay, but you are trying to innovate in the data space, you have to deal with variety. So that's the V in big data that we are going to be focusing on. Okay, so even though the class says something like big data analytics, maybe we could say something like big data analytics and put in the bracket, just the variety aspect of it. Okay, that's the main thing. And again, so we have all this kind of bunch of stuff, right? So that's the thing that we would use to analyze, and we would do it with Mathematica. Okay. Now let me create a little note just to so I don't forget, or you don't forget. Okay. Distinction, mathematical function, sine, cosine, exponential, logarithm, right? And then Mathematica function. Okay, so these are the guys that what? Oh, am I sharing? Yeah, I'm sharing screen, right? You can still hear me, correct? Even though นะครับพี่ต้องกลับไปเสียงเหมือนเดิมป่ะ เสียงแบบoh this is fine
This is fine ได้ยิน
okay same as before okay so I don't have to revert to my okay so built-in function i.e. yeah i.e. does with capital letters okay and so in Mathematica so let's create something new document okay just type something okay if you have a big plot okay so you can see it's going to give you sort of like auto correct or auto suggest now once you type that in it will be in black because it recognizes okay not only in black okay and then Mathematica user defined function i.e. blue until the program recognizes. In other words, so if I say my function x equal to x plus 5. Okay, notice it's blue. Okay, because it doesn't know it yet. But when I do shift enter, it recognizes. So it can be used as if it's built in. Okay, so it's blue until the program recognizes it, makes it black. Okay, so those are the three kind of functions that you'll be working with. Okay, this is common to the universe. This is common to everything you want to do with built-in function. But when you want specific instruction, like take a look at this data and do something with it, you are going to use the user-defined function, which is basically created from all the above. So you can think of Mathematica function as based on mathematical function, and then user-defined function as based on all of the above. Okay? So, both can be used to build below. Both can be used to build below. Okay? So let's make that note. Good. Now, having understood that, I'm going to give you what's called language primitives. That's something you already start to see, in the expression in the video. But in this note, I just want to make sure that you understand. Okay. The most important one, the first primitive you run into is equality sign. Now, those of you think you understand equality, actually there are three different definitions of equality. In Mathematica, if you write this equality, you are making it equal. So in other words, this is not called equality. It's called assignment operator. Okay, so this is actually looks like an equal sign. Okay, looks like an equal sign, but it's actually what's called assignment operator. Okay, so maybe I can. Okay, assignment operator. Okay, looks like this. Okay, so in this case, I'm not asking anybody. I'm telling you x is equal to 1. So when I type it, yeah, x is equal to 1. Notice that there's every line has a little bracket to it, so you can copy the whole thing just clicking this. You don't have to, do this. It's an input, and there's a number of how many computations since you started the program. So if I do it again, I input this again, it becomes 3. Output is the result of what you did. So you ask the computer to assign x equal to 1 and then tells you it's equal to 1. Now, for a lot of assignment, you just want to make the assignment and you want it to be quiet. And this is the way of turning it quiet. Just put in semicolon. Okay? So, yeah. Now you still get that x. You still get that x. So if I type in x over here, shift enter. Okay. By the way, I want you to replicate this. Just follow all this in your note. Okay. So I don't want you to just look at me or the screen. I want you to start your own Mathematica and type it along. So you should be typing x is equal to 1, shift enter. Okay. Right. So this x will always be equal to 1. Okay. Now it becomes like synonymous. Now, if you want, again, if you want to erase this memory, you have to clear it. So clear x. Now, if I do this, clear x, look what happened. Let me highlight this. X is now blue. See, it's unknown again. So anything that's not known to Mathematica, okay, or you haven't instructed it, you're just kind of like writing on a piece of paper. It's blue. Okay, so Mathematica doesn't know what x is. It knows what equality sign is. It knows what 1 is. It knows what this is. This is all black. It doesn't know what x is. Until you shift enter, then it becomes black. Yeah, it recognizes. Okay, so the color will tell you whether or not it's already understood by the computer. Okay, x is equal to 1 gives you that. Okay, this I can just erase. I don't need that. I'm not going to clear it. I'm just going to keep it. Okay. Now, this is the first thing. The first thing you need to do. Second thing you need to do is the most common data structure. In other words, list of things using this thing. Okay. So this is how you define set. But this is a very high level. It's just a collection of things. List as a collection of things. Okay, so let's say one or more. Okay, mostly more. Okay, you can have single thing. For example, I have this. Let me not spoil the surprise. So I'm gonna delete all the output. Okay, so you don't see the surprise. Okay, so once again, I put this in a bracket. 1/2 a pi. A is blue because it doesn't know what it is. This is a string. This is the word blue. Now shift enter. What Mathematica is going to do is try to recognize what you want to say. Automatically, it interprets this as 1/2. Again, infinite precision is 0.5, but there's no point, so 1/2. A is just something that it still does not recognize, so it just echoes back. So like A, that sort of thing, right? You give it an A, and it doesn't know what it is, it gives you an A, okay? Pi, it gives you this, but it does know what it is. It does know what it is. For example, how do I know that? Because if I type in A, I get this. But if I type in pi, oops, sorry. If I type in pi, okay, and remember number, oops, number, give it a pi, okay, default precision, I give 100 precision, gives you that number, okay? So it knows what pi is because it's universal. Now, if you don't give a precision, it's just going to give default precision, which is set to like 5 decimal. Okay, fine. This is just a sentence. It interprets this as the color blue. In fact, if I click on it, it brings on this thing because it recognizes it is a color. This color is defined by RGB value of 0, 0, 1. Okay. Now, what happened when I alter this? Oops, sorry. Okay, see, I just alter it. Okay, let's go put it back to blue. So this list here is a collection of things that are not necessarily arbitrary collection of things. Okay, it's just arbitrary. Okay, so it allows you to deal with things. So like you saw in the video, Mathematica can deal with variety of data. So you can imagine that instead of just putting this, I can actually put a video file in here. Okay, I don't have a video file right now, but I can certainly put a video file in here. It would just be one of the things. Now, if I want to refer to specific element from a list, you use this thing, double bracket. Okay. For example, this is a list, right? So let's name it my silly list. Okay, let's name it my silly list. Oh, okay. Oops, sorry. Okay, my silly list. And now I put in left bracket one time, two times. Okay, two of them. And I want to say element, the third one, 1, 2, 3, 4, 5. Let's say 5. What do you think I'm going to get? Now notice when you type in double bracket 5 and double bracket, it converts into this nice little shape. Shift enter, blue. Okay, so let me check. I'm not going to check. Just to again, one of the feedback I get is I tend to speak very fast, but unless you stop me or slow me down, I will just keep going. Okay, so I rely on the TA to spot. I guess the chat comment. If you say please slow down, just holler. Okay. Anyway, so you should be able to do this. Okay. I create a list. I make this. Now, of course, it has only 1, 2, 3, 4, 5, 6. So if I want the 7th element, it doesn't. Part of 7 does not exist. Okay, fine. Okay. So now, let's look at some built-in function. Okay. Miscellaneous built-in function, some of which are universal mathematical. Yeah. Now, so let's see. This is my built-in function, some built-in function. So this function is called a beep. It doesn't do anything. You don't need to give it a sign. It's just going to give a sound. Sine of pi over 2, power of 3 to the 3. Let's see what you get. Okay. So this is the sound. Now you can adjust the sound, but it's not important right now. Beep. Not interesting. Sine of pi over 2 is 1. Power of 2 to the 3 is this, right? You can also write it with the palette. Math Assistant. You can go to some of this, right? And then you could say 2 to the power 3. Same thing. So power has a shorthand. So some of the built-in function has a shorthand. In fact, let me go back to here. Some of the above have shorthand. Okay? Now, below here, you don't have shorthand because obviously you're creating it yourself, right? You have to name it. Okay. You guys with me so far? I'm making the assumption. So the list, of course, can be used to register the output. That's not very interesting. Here are more function. Logistic sigmoid function is a built-in function. Now, what's cool about Mathematica is that it's so smart. It recognizes this as a natural number E. It also recognizes this as infinity. Okay. So whereas in most mathematical texts, you have to do something like this. You have to do something like in the limit x goes to infinity, yeah, compute f of x. In Mathematica, you just do this and if it makes sense, it will give you that. Okay. So there's a symbol for infinity here. There's a lot of special character. Okay, so infinity is in here somewhere. There it is. Okay, infinity. Okay. Notice that if you don't know any better and you want to look up special symbol, it would also tell you your shorthand for it. So escape, INF, escape. Okay. Notice here, see on the bottom of the screen, on the bottom of this yellow thing, it says escape, INF, escape. We'll give you that sign. Okay. So next time you don't have to fish through the palette. Okay. So it turns out that this number actually makes sense. It's equal to 1. Okay. And you don't need to know what it is. You'll know it later. Okay. So if I do this, before beep just gives you the sound, it doesn't give you a number, so it gives you out now. Here, log of E is 1. E to the log anything is equal to the thing itself. Okay. Same thing as log of E to the power A. That's okay. Oh, for some reason I used the wrong E. Never mind. Okay. It should be the same. I don't know what. Okay. Now this N was the thing that you saw in the video. Okay. This is to force numerical approximation. Was use N. So E is a natural number. It's what's called transcendental number. Okay, it goes on infinitely. But if you put N to it, it would have to give you an approximation. Okay, so let's get a 500 approximation. Now, I want to take this opportunity to show you different shorthand. This is functional programming, yes. So you need a function and you need an argument. Okay, so this is a function. It always looks like this: function and then argument, right? But sometimes when you only have one argument, instead of putting a bracket, the reason you put in a bracket is very nice because you can put in multiple. Some function, for example, uses a and then 10, right? So it automatically uses 2. But if you're just using 1, alternative way is to say apply n to a. This is called pre-apply. So n to the left. The other one is called post-apply. Take a and then apply n. Okay. Now, you will notice that this thing is exactly the same. Sure. Now, this you have more than precision. Notice this is your E, right? I want numerical value of E. I can call it as a function. I call it n at E, or, right? Okay. Now, what is so cool about it is this. If I put in infinite precision, what do you think it's going to give you? If I give you 100 precision, 1,000 precision, it's going to give this, right? What if I want infinite precision? Well, how do I give it infinite precision? Escape, INF. Gets back to E, because you can't be more precise than that, right? So that's what this means. Okay, this is E without forcing approximation. This is forcing approximation with the default precision. This is 1 precision, 1 significant digit. This is 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, not number of decimal, number of significant digits. This is infinitely.
Please slow down a little bit.
Okay.
Some students do not catch it.
Yeah, please. Okay.
Sorry to interrupt you.
my bad. Okay, once again. Okay. Mathematically, I hope you guys know what E is, right? E is approximately 2.71 something. It's the number that you cannot write as a ratio. It's called irrational number. It comes from nature, okay? If you believe in creation, then it's one of the parameters that was created, okay? But anyway, it's a universal number. It shows up everywhere. That's called E, okay? So E, transcendental, okay? จำนวนอดิสัยของมัน E is transcendental. About the number E. Right. So okay. If I want a Wikipedia page on it, Euler's E. I guess we call it Euler's E. Okay. E, mathematical. Sometimes it's called Euler's number. By the way, that's why it's E, because his last name is spelled with an E. Okay. So if this guy's name is Smith, then you might have the little s. But this is the number. This number has infinite precision. Okay. Just read about it in your spare time, just for fun. Anyway, the point is, Mathematica understand symbolically that, okay, this. I think it's exponential. This guy, EE. Yeah, this is EE. Now this number, okay, Mathematica knows what it is. Therefore, it's not blue, it's black. But when you enter, it just gives you echo, because this is the most precise way of saying what that value is. Now, if you want approximate value, you have to say n, approximate value. Okay? How many significant digits? Let's say I want 20 significant digits. So 1 significant digit followed by 19 decimal. Okay. Now, this is the way of writing a functional programming. Please do something with this and this. That doing something is giving an approximate value. numerical approximation of this thing using 20 significant digits. Now, this argument, sometimes people can omit it. Some function allows you because it has a default. The default of this is 6. Okay, 6 significant digit is the default. You can probably change it later, but okay. If I didn't put this number 6, it's going to give you the same thing. Okay, so one way of checking is with equality, but I put double equality. Okay, this is checking inequality. True. Okay, so remember one. Okay, let me write this distinction. Distinction you learn today. Mathematical versus okay. So it's 1. What else you learn? 2. Equality sign is an assignment operator versus double equality is a Boolean operator, meaning it return true or false. Okay, distinction you learned today. So you learned 2 things already. Distinction. Okay. So is it true? Yes.
How to make a suggestion in Mathematica. For example, when you type PL and it suggests plot.
It should. Oh, you mean autofill?
Autofill.
It should be autofill. So let me write something silly like NO something. Yeah. So it makes a now n. It doesn't make suggestion because n is already a function. But let's say NA, right? There's name. There's okay. So as long as you do this, you can go down and maybe there aren't that many. So name Q, Nakagami distribution names. You know, Mathematica has thousands and thousands of functions. Okay, so it's going to make. So let's say NAM. Now it makes the suggestion. The suggestion narrows down, right? NAN. Okay, there's only one. Right? So that's it. Okay, just key in.
So it automatic.
Yeah, it's autofill, auto suggest.
Auto suggest. Thank you.
It's not. I don't know if it uses some kind of frequencies. You know, like what's the most frequent up top or ranked by. You know, it may do something like that. Like autofill, it just gives you the most common suggestion. Okay. So that's that. So this is useful because sometimes writing this is a little bit clumsy. You know, if I have a lot of function, I can put this function inside another function. There'll be a lot of bracket. You know, you can think of it like this: f of x, and then f1, and then f1, and then f2 of 2 of this, and then f3 of this. Okay, and then you have, it doesn't look very nice. So it would be the same thing as f3 apply to f2 apply to f1 of apply to x. Yeah, and also the same thing as x apply to F1, and then apply to F2, apply to F3. Notice the order matters. With this thing, you have to put a bracket around it because sometimes, okay? Otherwise, if things take the whole thing in front. Yeah. So this is something good to keep as well. Okay. Now. I think I have notes on this, but I'm not sure where it is, so I'm just going to revise it. Now, by the way, if you don't define A and B, instead of giving you false, it just echoes you back because it doesn't have enough information. You may secretly set A to 7 and B to A, in which case it's false, but you can also secretly set A to 7 and B to 7, in which case it's true. It doesn't know any better, so it just echoes back. Not very interesting. But certainly you can do something like A plus B equal to B plus A, okay? Or A times B plus C is equal to AB plus AC. Now, oh, this is false because it thinks AB is a name, so give it a little space. Okay, it still doesn't know what it is. Okay. Okay. Okay, but you certainly know. I don't know if it does this. Yeah. Okay. So these are both true. Okay, fine. Checking inequality. Now, approximation. So these are all primitive. Okay, this is clear. Okay, I clear X. Clear all X. Yeah. This is just to remind myself. In my lecture notes, I would put the gray highlight just at the end of the Okay, this is random seed, and never mind. This is called random. This is a global variable that I tend to set. Just ignore that. Now, here's an interesting thing. Here's a function. Okay, this is to create a list of items. Okay, with specified property. Okay, I'm going to use function called table. In fact, I'm just going to write this. This is very useful. Table is to create a list, right? Now, before that, I created this list. You guys saw this, right? This list of arbitrary subject, arbitrary collection of things. But what if I want to make a list of numbers? Okay, I want to make a list of numbers. Say 1, 2, 3, 2, 3, 4, 5, 6. Right? I can do this. I can do this, right? This is a list of numbers. Fine. Now, if I want to do this to 100, okay, it's going to take me forever, right? So there's a built-in number. I think it's called range. So that gives you that. So that's nice, right? So that gives you a list of numbers. Okay, that gives you a list of numbers. But what if you don't want to just list a number to 100? You want to list, say, okay, let's make it a bit smaller. Okay, I don't want to list a range from 1 to 100, right? I want a list of 1 to the power. I want to do something to it. Okay, I want to do something with it. For example, I want to plus 5 or sine of this, and then sine of this. Okay, I want to apply some function to it, right? How do I do that? Well, this is what I do. Instead of doing this, I make a table of some function. Okay, some function. So I haven't specified any function yet. Function of I going from I to 10. Okay, so if, for example, function of, okay, number of 1 over I is going to give 1, right? See that? Okay. Well, actually, if I can do this, it's going to give you this, right? So that maybe that's a bit more obvious. Okay. So now I don't want to start from 10. I want to start from 5. Click here. Guess what happens when I start from 0? No good. This is called complex infinity. Okay, so that's no good. So table is very useful. Okay. Now, if I want to create not a function of a list of number, and I just want a many times, this is what I get. So see, table of A's. It doesn't depend on I, so it just makes it 10 times. So this is good. This is b to the I from 1 to 10. B to the I from 10 to 20. B to the I from 10 to 20 instead of 3. Okay, so look at this. So I want you to type in. Okay, now for this, you can do this, right? B and I. It's the same thing. Okay. So try this on your own. Table of A. So table creates a list. Okay. To create a list to create a list by enumerating by enumeration instruction. That's a little bit short. By the way, guys, table is going to become your best friend. Why? Because in most of this class, even though you're working with picture data, photo and sound and so forth, the first thing you have to deal with is tabular data. And what is tabular data? It's this thing. Okay. For example, I may have, let me just say random number. Okay. I just make this random number up. If you think about it, this is one data point, second data point, third data point. If you're not convinced, I'm going to put it in table form. See? Now it looks like one column, right? Right? Now let's do something else. I'm going to create this. Now, the reason, because it's random, it doesn't mean anything, right? It's just some kind of random integer, maybe from 1 to 10, I guess. Okay? Right? You can see that this table form looks like what? Looks like data entry from the Excel. Okay? So the table data structure, even though it's written in bracket, It looks like this, by the way. It looks like this. Okay. But if you format it, this is a function that does nothing but putting it in a nice format. Table form. Okay. Format. Okay. But basically, this is the sort of data you're going to be working with. Okay. Data that appears on Excel or something comes in this kind of table form a lot. So this table function, now here you are generating the data, okay? But in reality, you might do something like take some value and then multiply by 5 and then add it to another column, whatever, okay? So you're gonna see that a lot. So maybe I can put that.
May I interrupt you?
Yes, please, of course. Please
Okay.
interrupt.
When you type something into one cell, like this one, maybe that one,
Yeah.
this one. How can you make another cell when you type it?
Okay. If I type this, okay, if I type this, let me see, I type this. Okay? I go to some empty spot and I type this, and I shift enter, it's going to give the result. Now, if I don't shift enter, if I just enter and I put something else, it's going to do both of these. It's going to do both of these. So when I shift enter, that's the first line first, followed by the second line. That's it, just sequentially, right? Do this, then do that. Now, if you don't like to see the output, you can suppress it with the shush. In which case, what would happen? It would just show this, right? Alternatively, I want. So notice that it executes the whole kernel. This is called kernel. Okay, kernel. Okay. This is how Python copies the mathematical way of writing. The Jupyter notebook copies the mathematical way of writing kernel. Okay, so this is the sort of like, don't show, just quiet with the sh sign. Okay, now like this, because I didn't shift enter first. If I shift enter, I just get the result. If I enter, I can put in an instruction, right, and get both results. Okay.
Oh, so this one will be here, and this one will be here.
That is correct. Just sequentially. Okay. Now, of course, if I put in something else, C, and I make this guy silent, what's going to happen? It's just going to show A and C, right? So this is the sh sign.
Okay, thank you.
Okay,ครับ. Now, there's another thing called matrix form. Maybe I should put something like to display table or matrix. Okay, so there are two functions here. Table form okay, matrix form. So let's just say okay. Let's make this 5. Okay, so right now it's like this, right? Doesn't look nice. So it's a list. Notice, okay, let me show you first what I mean by this. It's a list of lists. So this is the first element of the first data, second element. First, second. So you can see this bracket, right? So this bracket is one data point. This bracket is another data point. This bracket is the whole data set. Okay, so you can think of this as one row, the entire two rows, or the columns. Sorry, let me say that again. This is the first row, this is the first column, second column. This is the second row, first column, second column. All this is 5 rows of 2 columns, but it's hard to see. It's not nice. It doesn't look nice, right? It's convenient mathematically, but it's not nice. So let's make it table form. Usually I put in the back because formatting is not something that means a lot. Okay. So that's the table form. Now let's do this, but I'm going to use the word matrix form. Let's look like this. So it looks a little bit like table, but it has this kind of bracket. Now this is something you will see in linear algebra as a notation. In this case, you would think of it as a, anybody? 5 by 2 matrix, right? 5 by 2 because it has 5 rows and 2 columns. Okay. So if I put in something else, like put in some funny text. Right there. Yeah. Then this becomes a second column, but it's a column of text. It doesn't mean anything. Okay. So maybe I should do this. So that's the first I, right? And random integer and random real. Okay. Maybe random integer 10 and 20. Okay. Or -5 to 0. Okay. -15, -20 to -10. Okay. That's all much. So that maybe here. Now, by the way, notice that the values are not the same. This is 12, this is 19, because what? Because I re-randomized, right? But if I did this, okay, random seed, 1, 2, 3, 4, okay, and then do this. I'm going to get the same number. Random seed is sort of like starting a random sequence. So notice -12 and 2 to 6. Something is not right. Something is not right. Hold on. Okay, I have to go figure out what happened. I think I used this function wrong. Okay. Sorry about that. Anyway, so this is list in matrix form. Now this is actually, and from now on, I'm going to assume that you know linear algebra. Hold on. Not cap. Look at the students and raise your hand if you don't know what a vector is. Huh? Yeah, how many people raise their hand? Right, Cap? How many people raise their hand? People who don't know what a vector is? Right, Cap? Hello? Are you with me? Oh, I've lost people. Anybody? Raise your hand. Raise your hand if you don't know what a vector or a matrix is right now, because otherwise you're going to have a difficult time in this class. Okay, if you don't want to raise your hand now, but you actually don't know, do communicate that with your TA. It's very important. It's very important. It should have been covered in your year 1. Okay? So let me go back. Okay, so I'm using a list to represent a vector. Well, a vector, right, it's just a list. The dimension of the vector is equal to the number of elements. By the way, okay, if I want to know what the length is, length of that. Three, right? The length of the list, okay, i.e. Okay. This, by the way, if you put, you can see that the light green is the way of putting comments. Okay, so it's just a comment. It's equal to the number of elements of the length. Okay. So if I put the length of this, if I put length of table of A from 1 to 155, what am I going to get? Okay. Yeah. So this is basically a vector. Now, a matrix is an array. It's a rectangular array. So it's a list of lists. Okay. Now, all this is displayed using matrix form. Right? Matrix form. Now, earlier, I show you what application, right? So matrix form of X, instead of doing that, I can do this, right? But what if I want to do this, and then this, and then this? It's a little bit clumsy. It's a little bit clumsy. Yes. Instead, what I'm going to do is like that. You follow me? Okay. Apply this function to this one at a time. Now, because it's not applying to the whole set, you have to add additional notation to say you are applying it to a list. It's the exact same thing. Exact same thing. So this is another notation. This is a shorthand. So how many shorthand have you learned? F x versus what? F at x is the same as an x f. Okay. Now you also learn that f, okay, apply x, y is the same as list of f, x, f, y. So this is a shorthand. This is a shorthand. I actually write it in the notes somewhere as a shorthand. See? Oh, I already did. Sorry. Okay, it's already here. As a shorthand, you can equivalently use this to pre-apply matrix form to a list of targets. Okay. So let me write a heading for that. Shorthand for applying function to a list. Okay. So yes, name of function, okay. Name of function, apply to a list, one at a time. Now, you can do scalar multiplication, vector addition. By the way, all I'm doing is show you what this looks like, but I'm applying in matrix form. Now, this is important thing. This is a dot product. Okay, a dot product. Anybody? Dot product, aka inner product, aka cosine. Okay. Now, once again, please raise your hand if you don't know what a dot product is. Okay, let me just write real quick in a, okay. Okay, if I have this thing, this thing, this thing is a row vector, and I multiply by this thing, this thing, this thing. Okay, now you take this thing, you multiply by that thing. You take this thing, you multiply by that thing. You take this thing and you multiply by that thing, and then you add them. Okay, that's called dot product. Now in Mathematica, because you write it like this, you would put bracket dot. Okay, so let me show you. So A, B, C dot 5 to 5, 10. Okay, let's do that. Okay. Now, to the left, it's like a row vector. To the right, it's assumed to be a column vector, but you write it like this, it's convenient. So what it's going to do is say 2 times A plus 5 times B plus 10 times C. Now, notice it's different from this. This is ordinary product. This is going to try element by element. 2 times A, 5 times B, 10 times C. Notice it's a different thing, right? So notice it's nothing. This is like multiplication. Okay. Mathematica, when you put in a bracket, sorry, when you put in a space, it knows. It knows. So stare at this. And write down in the note. Element by element multiplication versus dot product. Okay? Okay, so this gives you what? This is an element by element multiplication. This is assumed to be dot inner dot product between left hand side column vector and right hand side row vector. Now, if you don't know this, you need a review in linear algebra, which is not going to be covered here. Okay. But do contact me or your TA if you need a little refresher. But you definitely will struggle, by the way. I'm not suggesting you drop the class, but if you don't have good working, if you're not comfortable with linear algebra, you're going to struggle in this class. You're going to struggle in this class because data comes in tables. To operate on them, the very basic thing you need to do is be able to add and multiply. And to be able to add and multiply table of numbers or array of numbers, you really need linear algebra. Okay? So go. Yeah. Oh, for some reason I have X and Y already. Okay, so notice if I have X and Y, X, Y, okay, I get this. But if I have X plus Y, X dot Y, I get this. So maybe I should put this separately. Okay. Element by element multiplication. Now, the only thing that we require is that you don't need to write anything, right? You just put a bracket. Okay? Or multiplication sign. You don't really need that. Okay? Just put it. So dot product here. For convenience, the dot product. Okay? On left hand side. Note that Y is already upper column. Okay, so there. So this is a list of element by element multiplication, but now, is it the same thing as doing this? If I'm going to add this, right, add the element, The element happen to be a number, okay, from the number. So if I do this, if I total, right? So my question is it the same thing? Total X and Y is the same thing as that. Now, I'm going a little bit fast, but you can see, right? So this is element by element. This is dot product. Well, element by element multiplication is also useful, but dot product is a lot more useful. Okay. Okay. Now, by the way, let me just instead of checking using the and notation, let me just make a note here. I'm going to say yeah. What it does is check the left hand side, check the right hand side. Right. So using a list of lists to represent matrix. So this is more advanced, right? So instead of having this, it's a list of lists. And so let's see what it looks like. It looks like this. So let's multiply matrix. Let's represent this in matrix form. Multiply A and B. By convention, matrix is used, you use capital letter. Okay. Now you can also do table form, but table form is not going to be nice. So when you work with data, sometimes you work with data form with table form because it comes in table. But when you're ready to do heavy duty multiplication, manipulation, you tend to go to linear algebra, in which case matrix form becomes the norm. Okay. By the way, so this is just to show you, this is multiplying element by element. Now, you can put lambda to the left hand side, the right hand side. Transpose, you know what the transpose is, right? Transpose. And let me do this as well. Let me just add inverse of A, just in case you are interested. Now, raise your hand. Okay, so let me check 5. Recall vector matrix, right? Dot product. Okay, dot product matrix transpose matrix inverse. Okay. So you have to do this, you have to recall this, okay? So, how many of you guys, well, let me just relax a little bit, not relax, pause a little bit, and look at your facial expression, see if you're with me so far.